Okay, we continue our theorem 2.15 quotient property. So it says, suppose the limit n approaches infinity of an equals a, and the limit n approaches infinity of bn equals b. And here bn is not equal to 0 and b is not equal to 0. Then the limit n approaches infinity of an over bn is equal to a over b. Okay, so this is the quotient. So the proof, we use the proposition which is 2.14. You can look at your notes. Okay, so we write this quotient as a product we write this one as 1 over bn times an, or an times, well, doesn't matter. Okay, then we can use the product property. Okay, this is the product property. That means you can take the limit for each one if each one exists to have the limits. Okay. And then the next step is, which is equal to b1 over b times a. A, this limit equals a, no problem, but this limit equals 1 over b, which is the proposition 2.14, okay, which is the previous one. Then you have this a over b. Okay, then we finish the proof. This is very quick. Okay, so we have the theorem for the sum, right? For the product, for the quotient of convergent sequence an and bn. So now let's look at which is called the linearity property. Proposition 2.16. which is called the linearity property. This says the limit n approaches infinity of alpha an plus beta bn is equal to alpha times the limit n approaches infinity of an plus beta times the limit of bn. Okay, so then we can use the sum and the product properties to prove this one quickly. Okay, so here the proof I will not see. We can use the sum and the product. Right, product. We also have a lemma that says you can take the constant outside. Right, product properties. Okay, I will skip the proof because it's very straightforward. Okay, so now let's look at what about the polynomial. So now let's look at this one. We let p be a function which is from R to R. This one p is defined by the following way. P of x is equal to the summation I from 0 to k. Okay, and here ci is any constant, real constant. Okay, and times x to the I. So this one can be written as c sub 0 plus c1x plus c2x squared plus c sub k x to the k's power. Okay, so here x is the real number, and this kind of form is called the polynomial. This P is called a polynomial. Okay, then we have the polynomial property, which says the polynomial is the sum of each term, right? If you take the limit and approaches infinity for the, okay, so let's look at this proposition. 2.17, which is called the polynomial property. Okay, so we say if an is convergent to A, this is the sequence, okay? Then for any polynomial P, which is from R to R, okay, so we will not consider anything in the complex, okay, domain. So R to R, and then for any this kind of polynomial, if you take the limit and approaches infinity of P of an, then you can pass the limit inside, so it becomes P of A. Okay, so the proof is still quite easy and straightforward. So this one is the, let's look at the quick proof for this one, and what is P sub an, which is equal to I from 0 to K of C sub I an to the i's power, right? So if you take the limit and approaches infinity of P sub an, which is the limit and approaches infinity of the sum I from 0 to K Ci times an sub I, right? So it's equal to, since this is the finite sum, so you can use the sum property, right? You can sum property instead. Okay, we can take the limit for each term, right? So this is the sum I from 0 to K, and this is the limit and approaches infinity of Ci times an to the i's power. Okay. Then we use the product limit again, right? Product property. So this is the i's an, the product of I an. Okay. An times I times, right? So you can use the product property to take the limit for each one. So this is it's equal to the summation I from 0 to K, and this is the Ci times limit n approaches infinity of a sub n to the i's power. Right, so this would be equal to summation I from 0 to K. This is Ci times a to the I. Right, then we finish the proof. Okay, which is exactly this one, right? Which is equal to P of A. Okay, so we finished the section. So this section we have many techniques, okay, especially to how to use the n epsilon language or n epsilon n language to prove this, to prove some limits, okay. And the proof in my notes are different from the proof in your textbook, okay. So I think you'd better to use my proof, okay. Okay, so now let's go to the next section, which is called a sequence and sets. Okay. Sequences and sets. Okay, so let's look at the definition for, say, the definition for the bounded sequence. Okay, what's the meaning for the bounded sequence? So we say sequence AN is bounded if there exists a number m which is greater than 0, such that this AN, take the absolute value, is always less than or equal to this m. This is for all n. N is from 0 to infinity. Okay. So this is called bounded. So it's always bounded by a constant. Okay. If you take the absolute value, it's always be less than or equal to this. If you can find this number m, then you can show, okay, this one must be, the sequence must be bounded. This is true for all n. Okay, not just for the capital greater than capital N. Okay, it's for all n. Okay, so now let's look at this very important theorem. And the proof have some techniques you will see in the future. It says every convergent sequence is bounded. Every convergent sequence is bounded. Okay. So the one thing I should say is that the other way is not correct. The bounded sequence may not be convergent, but the convergent sequence must be bounded. So now let's look at the proof. So we let the sequence AN converge to a number A. Okay, so this is a convergent sequence. Okay. So now we need to look at the definition for the convergence of sequence. That means for any epsilon greater than 0, there exists a capital N. Right? When n lowercase n is greater than or equal to this capital N, this AN minus A should be less than epsilon. Right? This is the definition. Okay, so we want to use this definition. So it says for any epsilon, let's take 1. Okay, let's take one value of for epsilon. For example, let's take epsilon equals 1. So let's take epsilon equals 1, right? For any is true, so we just take 1. We pick 1. You can pick 2. It doesn't matter. Okay, there exists a capital N for this epsilon, which is equal to 1, greater than 0, such that, right? This is the AN minus A is less than epsilon, or which is equal to 1, right? Epsilon equal to 1, so less than 1 for n is greater than or equal to this capital N, right? So now we have this inequality. So we want to use this inequality. So here is one inequality we want to use. You have learned and you have proved in your homework. Okay, which says this one is less than the absolute value of AN minus A, the absolute value of it. You remember that homework. Okay, the homework you have this kind of inequality. So this one is less than 1, right? So we have AN, take the absolute value, is less than 1 plus the absolute value of A. A is a fixed number. Okay, A will not change. So this is true for n is greater than or equal to capital N, right? So in other words, when n is greater than or equal to capital N, all the numbers, all the sequences, okay, all the numbers in the sequence is bounded by this number. What about n is less than lowercase n, capital N? We remember we need to find this m, the bound m, okay, m here, for all n, not just n greater than or equal to the capital N. We need it for all n. But the good thing is, greater than n is always bounded by this number, okay? What about n is less than this n? The good thing is that less than n, we have finite terms, right? A0, A1, A2, A3 to A capital N. If we can take the maximum value of this n and this number, then we're done. This is our m, okay? So this is the idea. So we let our m to be the maximum value of what? For greater than n, greater than or equal to n, it's bounded by 1 plus the absolute value of a, right? But for the other terms, which is the finite term, which is the a1 term, right? A2 term, we can take a1, take the absolute value, a2 to be x, and to the an minus 1, right? Less than n, so it's up to the n minus 1. We take the maximum value for these n numbers, right? Because these numbers are finite number. We can always take the maximum value, right? A1 is a finite, A2 is a finite, is a number, right? There. So to n minus 1 is still a finite number. After that, we can use this one, 1 plus absolute value of a, which is the upper bound, right? The upper bound for the rest part. So there are n numbers. So this is the finite numbers, right? There are n numbers. So we can always take the maximum values. So we take the maximum value of this. We choose this one to be our m. So this an is less than or equal to this capital M. Right? It's obvious, right? For all n. Right? So this am is the maximum value. So it must be greater than or equal to the absolute value of a1, greater than or equal to the absolute value of a2, right? Greater than or equal to the absolute value of n minus 1. And how about an plus 1, which is always bounded by 1 plus a.
Why do you have to pick your epsilon to be a number? You just keep it as epsilon?
It's because we know this converges to a, right? Which is true for any epsilon, right? Any epsilon. So we just take one. You take one value for this epsilon, right? You can take 2, you can take 3, it doesn't matter. You can take 1/2. We just need fix one, okay? Fix one epsilon.
Okay.
Yeah, fix one epsilon. So you see here is 1, here's a number, right? Will not be an epsilon. Epsilon will be changed, right? If you don't fix the epsilon, it would be changed, right? You can say nothing, right? Yeah, so you need to take epsilon to be a specific one.
Okay. You can just say it fix epsilon or fix e within epsilon.
Yeah, you can say, okay, fix epsilon. Yeah. Okay, you should give me some numbers, right? Okay. Yeah, you cannot just say here is epsilon, right? Of course, you should say, okay, epsilon is a fixed number. That's fine, but this is not very obvious for the readers, right? Okay, so this is the proof. So you can see this kind of technique we often use. Sometimes we pick some special numbers, not special numbers, some specific numbers for epsilon. Okay, this is one thing, and sometimes we will take some maximum values, right? So this is the two techniques you will see in the future. So now let's look at the remark. The remark, as I said, a bounded sequence may not be convergent. A bounded sequence, for example, this sequence. This sequence in my last lecture, I proved this sequence does not convergent, but it's bounded. It's bounded by 1, right? It's jumped from -1, 1, -1, 1. If you take the absolute value, it's always less than or equal to 1, right? Or less than or equal to 2, doesn't matter, but it's bounded, right? So this is bounded, but not convergent. Okay. So now let's look at the next definition, which is dense. Okay, so dense, I'll just repeat this definition again. We say a set. So we have we say a set is called to be dense in R if for any interval AB there exists a point in S belonging to this interval AB. So this is saying, okay, which is dense, right? We know that rational number is dense in R, right? Irrational number is also dense in R, but the integer are not dense in R, okay? Dense means almost everywhere. Okay, so now we want to, so the next definition, which says, we say a sequence is in the set S. Is in the set S. What does this mean? This means if every member, every x sub n, here n is from 1, 2, 3, and so on. All right. For every x sub n belongs to so every member in this sequence is a member in S. Okay. Every member in the sequence must be in S. So then we say the sequence is in S. Okay, so now let's look at the proposition. Proposition 2.19. We say set S is dense in R if and only if for any real number x, x must be is a limit of a sequence in S. Okay. If, okay, so this is called the if and only if problem. So that means you need to prove this result. You have two statements, right? On the two sides of if and only if. Right? So if and only if, that means these two statements are equivalent. Okay, they're exactly the same. They have the same meaning. So that means you need to prove this theorem with two directions. One direction is if you know the statement 1, you need to prove the statement 2. Another direction is if you know the statement 2, you need to prove the statement 1. Okay. So what does this theorem tell? A proposition tells you that if the set is dense, okay, give you some sense of the density. If a set is dense in R, then we pick arbitrary number in this R. We can always find some sequence in this dense set S, such that this sequence is convergent to this number. Okay, the arbitrary number. For any arbitrary number, you can always find some sequence in the set S to approach this number. Then this kind of set must be dense. Okay, so now let's prove it. So this is because this is the if and only if. So we needed to have 2 directions. Okay, let's look at this direction. This direction. So that means we suppose S is dense in R. Then we want to prove that for any X in a real number X, we can always find a sequence in S such that this sequence has the limit as X. Okay. So suppose S is dense in R. So this is the given. Okay, this is the condition we have. So now let's pick arbitrary X. So we let X to be a real number, any X. So now we want to use this density. Okay, S is dense in R. So since S is dense in R, so what's the meaning for the dense? Dense means for any interval, you must have 1, right? Element, at least 1 element in S. So that means since this one is dense in R, so there exists, we pick 1, X sub 1 in S, such that this X1 is in the interval. Let's just make this interval, okay? Make 1 interval, X plus 2, X plus 1. This X is given, right? We picked X. So this X is fixed. So X to X plus 1 is an interval, right? It's a real interval. So since S is dense, so in this interval, we must have at least 1 element in S, right? Okay, so we take an arbitrary 1. We denote this point to be X1. Okay. What about for another interval? We pick X2 in S, such that this X2 is in this interval. X to X plus 1/2. No problem, right? X to X plus 1/2 is an interval. Since S is dense, so X2 must exist, right? Okay, then we continue this way. There exists an Xn in S, such that Xn is in the interval from X to X plus 1/n. Right? Then you continue this way. Then you can form a sequence. So X1, we pick X1 is a member in S such that this X1 is inside X plus 2, X plus 1. We pick X2 to be the member in S such that this X2 is in the interval X to the X plus 1/2, right? Then we pick X3 in the interval X, comma, X plus 1/3. We pick X4 in the interval from X to X plus 1/4, and so on. We pick the Xn on the interval from X to the X plus 1/n. And then you continue, right? Then you continue this way. Continue. this way. We continue in this way. Then we form a sequence xn, because each member is in S, so this sequence is inside, is in. We form a sequence that in S, in S, such that this is the X, because the length for each interval is 1/n, right? So xn is between these two numbers. So xn minus x should be less than the total length, right? The reason is here is x and here is x plus 1/n, right? So the length for this interval is 1/n. 1/n, this is the length. If xn is here, you take the difference much less than 1/n. Okay, so this is the difference. This is the distance, right? It's less than 1/n. This is true for all n. Okay. Then we can use which is called a comparison lemma, right? This is inequality, and we know that this has a limit 0, 1/n. When n approaches infinity, it would be 0. So that means this one approaches 0. So in other words, xn should approach x, right? Okay. So we by comparison lemma we have learned in the previous section, and this fact, the limit n approaches infinity of 1/n equals 0. Then we can conclude that this xn approaches x. Okay, so this is the first part, right? The first part says, okay, suppose S is dense in R. For any x in R, we can find some sequence xn such that this xn is convergent to x. So we are done, right? So this part is a construction proof. So you see, there exists a sequence. So that means here we construct one. How do we construct, right? This is the process to construct the sequence. How do we pick x1? From x to x plus 1. How do we pick x2? From x2 to x plus 1/2, and so on. So you need to teach. Okay, you cannot say, okay, there exists one. You cannot say, okay, we can find one. No, this is not the reason. You should tell me. You should tell me, how do you find this one, okay? Right, this is the process to find this process, right? This is the process to find one. Okay, then using this process to find one, there is some properties for this sequence, right? So which is x minus x, xn minus x, it should be less than n, 1/n. Okay, then you can using this sequence, and then we can show that this sequence is convergent to this x because of the comparison lemma, because the right side will approach 0, right? It becomes smaller and smaller when n is large, right? The comparison lemma says, okay, if the right side approaches 0, then the left side also approaches 0, right? Okay, so this is one direction. So we need another direction. Okay. So the other direction says, okay, suppose for any x in R, this x is a limit of a sequence xn in S. Okay, so this is given. For any x in R, this x must be a limit of sequence in S. Okay, this is given. So now we want to prove this S is dense. So how to prove a set is dense? The only tool we have is the definition, right? So you will see that many analysis proof is always based on the definition. Okay, it's always based on the definition. If you have no tools, you use the definition to prove it. So now we want to prove this S is dense. So we need to use the definition for the dense set. Okay, which means for any interval, you can find one element in the set. Okay, so now let's pick arbitrary interval. Okay, let this AB be an arbitrary interval. Okay. So since this is true for every x, right? So now let's fix this x. Let's take x to be 1/2 of a plus b. We have an arbitrary set AB. Then we pick the middle point as our x. No problem, right? From the condition we have, from the assumption we have, this one must be a limit, must be the limit for a certain sequence in S. So by assumption, we have there exists a sequence xn in S such that xn is convergent to this x, which is equal to a plus b over 2. Okay. So now we have this one. So how do we continue? So now we have the limit xn, we have the subsequence. So now we want to prove that when n is large enough, this xn should be inside this set. Okay. So this is the idea we have. You can see. This is AB. We pick arbitrary interval AB, right? We choose a point. We want to show there is some elements in S which is in this interval. How do we show that? We pick the middle point. This is X, right? We want to show that since we have a sequence, okay, I use another color, sequence. A sequence which is converged to this X. So that means when n is very large enough, it would be around this X, right? It's called converged to this X, right? When n is large enough, then this xn should be around this X. So since it's around this X, it should be inside. When n is not large enough, maybe outside, right? Maybe outside. But when n is large enough, it would be around this X. Otherwise, it will not converge to this X, right? It should be around this X. Then this, if it's very close enough, it should be inside this interval, right? From the graph, obviously, it should be inside this interval, right? No matter how small the interval is, right? No matter how small the interval is, if you have a very small interval, very tiny interval, we still have the middle point, right? We still have the points nearby. Okay, but this is not a proof. You need to prove it. This is the idea, right? This will help you to understand why this is true. But you need to prove it, right? This is just some idea. It's just, okay, yeah, this is true. But how to prove it? When we prove it, we have to use the definition of convergence, which says for any epsilon greater than 0, there exists a capital N, right? That blah, 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 right? So now let's take a special epsilon. Let's take the epsilon to be b minus a over 2. You will see why, okay, later. B minus a over 2. For this epsilon, because it's for any is true, for this one must be true, right? For this epsilon, there exists a capital N greater than 0, such that x minus x, n minus x is less than epsilon for n is greater than or equal to this capital N. If we expand it, this inequality, what does this mean expanded? We just get rid of the absolute value sign. Okay, so this one would be x plus epsilon and the x minus epsilon, right? Okay, this is true for n greater than or equal to capital N. Okay, so what is x? X is a plus b over 2. What is epsilon? Epsilon is b minus a over 2. If you plug in other words, if you plug in, okay, a plus b over 2 minus b minus a over 2, which is equal to a, you can calculate. If you plug in here, this one plug in here, this one plug in here, it would be b for n greater than or equal to capital N. So you see, at least one, right? So x capital N, we just pick one. X sub capital N is in this interval AB. And x capital N is in S also, right? Because the sequence is in S. So for arbitrary, since this interval is arbitrary, so for arbitrary, that means for arbitrary interval, you can always find a y element in S. So which means S is dense. Okay, so this is the way. So if you choose this x, so why you choose this number? Because if you plug in, if you do the analysis, you see, okay, if you plug in, it's just the a, okay? Of course, you can choose other numbers. You can choose 1/4. Oh, not 1/4, one, yeah. You can choose some numbers to make this, the left side to be greater than a, the right side to be less than b. That would be okay, right? Inside this interval, no problem. But here, just perfect, a and b, right? Between a and b. Okay. This is the, okay, give you time to think about it. So this is the way we finish the proof. So when we have the if and only if problem, we needed to prove two directions. Okay. This is the first direction, from the left to the right. Then from the right to the left. This is the second direction. Okay. And in the proof, we have some techniques here. And you will see this kind of technique very often, x plus 1 over n, this kind of technique very often. Okay, you will see later in other proofs. So we needed to construct a sequence which is convergent to this x. You cannot not just say, okay, there must exist. You should show me why tell me clearly, how do you find this kind of sequence, right? And for this direction, okay, you understand if it's convergent. So that means where n is large enough, this xn should be very close to this x, must be inside this AB, right? Interval AB. But you cannot just say, okay, when n is large enough, there must be some numbers inside, very close to x, and then inside this AB. You cannot say that. You need to show me. I want to know why. Right? Although your graph makes sense, but why? You need to use the language, right? To tell me the reason. So here is the thing. You see, at last I have xn is between A and B. We prove that. Okay, you cannot just describe the situation you have on the graph. You need to use some math language. Okay, math language, not just the general language to describe. Right? It makes sense. Okay, when no matter how small the interval is, but since if you have some convergent sequence converged to the middle point, so it must be inside, right? Otherwise, it would not be convergent, right? But you should tell me, right? You cannot just say the words like I said here. You need to tell me just using this kind of language, math language. Okay. So this is the reason it's very hard to grade your homework. Everyone has a different opinion, right? Different proof. I needed to read your proof very carefully, right? Okay, so this is the theorem. The theorem is just a very quick theorem. It says this is called the sequential density. Sequential density of rational numbers, of the rationals. It says every number is the limit of a sequence of rational numbers. This is just very straightforward results from the previous theorem. The previous theorem says if a set is dense in R, if and only if for any number, right, in R, it must have a sequence convergent to it, right? Okay, so since this one is about the rationals, so we know the rational number set is dense in S, in R. So for any number in R, we can always find a sequence such that this sequence has the limit of this number, right? Yeah, just the one sentence. Because this is just a very straightforward, which is a direct result from the theorem, the proposition theorem. I forgot. Yeah, the proposition 2.19. Okay. So this is called the sequential density. Okay, we always can find a sequence approaches to this number, the rational numbers to any number. Okay. So the next one is about the closed set. Okay. What's the meaning for the closed set? Okay, before that, let's look at some results. Lemma 2.12. Suppose we have a sequence Dn, which converges to D, where D sub n is greater than or equal to 0. This is for all n. The result is then the limit must be greater than 0, greater than or equal to 0. Okay, so we needed to prove it. The understanding is very clear because you have this one, right? This is 0. If everything D1, D2, D3 is on the left side of 0, on the right side of 0, right? I use another color. Everything is on the right side of 0. So the limit will not be here. It's impossible, right? If the limit is on the left side, you must have something on the left side. It's called an approach to this number, right? But this is the contradiction to our greater than or equal to 0, right? Okay. So we needed to prove it. We needed to prove it. But this is not the proof, okay? It's clear, right? From the graph, from the geometry. We know we must have something. If this one is less than 0, we must have something on the left side of 0, right? This will contradict to our Dn is greater than or equal to 0 for all n, right? Okay, so the proof, as I said, we use the contradiction. Suppose our D is less than 0. Suppose D is on the left side of 0. Then we want to show that there must exist some Dn is less than 0. Okay? Since Dn is convergent to D. Okay? So what does this mean? This means for any epsilon greater than 0, right? There exists capital N. When n is greater than or equal to this capital N, Dn minus D is less than this epsilon. Okay, this is for any epsilon. Let's pick a special epsilon. Let's take epsilon to be the absolute value of D over 2. D is less than 0. We always take epsilon to be positive number, right? So we can do that, no problem, right? Okay. So why we do that? Because this is D. If this is D, take the epsilon D over 2. So this is the I use another color to represent this would be this idea. Okay, so we have some x Dn, sorry, Dn minus D is less than epsilon. So that means Dn is less than epsilon plus D, and Dn is less than D minus greater than Dn minus epsilon. It's centered with D, right? The radius is epsilon. The radius is epsilon. So in order to make this interval to be on the left side, right? After that, when n is greater than this capital N, this all the Dn should be inside this interval, right? So how to make this interval to be on the left side of 0? We just make this epsilon. Epsilon is the length, right? Less than D, less than the absolute value of D. From this D to 0, the distance is the absolute value of D. So we just pick a half, right? You can pick 1/4, no problem. So here I just pick 1/2. 1/2 of the epsilon. So it must be inside, right? On the left side, of this 0. Okay, on the left side of this 0. You can take 1/4, no problem. Okay, you just need to guarantee this interval should be on the left side of 0. Okay, so for this epsilon, there exists a capital N greater than 0 such that This dn minus d is less than epsilon for n is greater than or equal to this capital N. Okay, so now let's rewrite this inequalities. What does this mean? Okay, I give you time to write down notes. Okay. So this dn is less than d plus epsilon, greater than d minus epsilon. Right. For n is greater than or equal to capital N. How do I get this one? I just get rid of this absolute value sign, right? So if you get rid of absolute value sign, this is less than epsilon and greater than negative epsilon, then plus d on both sides. Then you will have this one. Okay. Okay, so this one, so let's plug in d. So this is d minus the absolute value of d over 2 dn, and this is d plus the absolute value of d over 2 for this n is greater than this capital N. Okay, let's get rid of the absolute value sign. So this d is negative. Remember, d is negative, right? We assume d is negative. So get rid of it, it becomes minus d. Minus d minus would be positive d, right? Plus d, not positive, plus d. So it's 3d over 2. Less than dn. Here's minus d. So d minus d over 2 would be d half of d, right? This is for n is greater than or equal to. Since this d is negative, right? This we know at the beginning, we assume, right? Then this interval, every number is negative number, right? Contains only negative number. So that means when n is greater than this capital N, then we have dn is, which means the dn are negative numbers, right? So in other words, dn is less than 0 for n is greater than or equal to this capital N, which contradicts to our this dn is always greater than or equal to 0 for all n. So that means d must be greater than or equal to 0. So d is greater than or equal to 0. Okay. So for some analysis problem, drawing a graph will be very helpful to understand, right? To understand the why, what you are going to do, right? So here we draw the graph like this one. We draw the graph. Okay, we say okay, this is 0. If we have d is here, right? We know if n is large enough, it should be around this d, right? Around this d. So around this d, that means it must be less than 0. So in other words, if you can prove that if you have some interval, right, around this d, after n, capital N, it's always inside. So we take this, the length, the half length of this interval to be the epsilon, right? Because this one is represents an interval centered at the d. Okay, so how to take the half length? How to take this interval to be on the left side? So you cannot make this length, the radius of this interval, to be too large, right? You should make this to be small enough. How small? Okay, we just take 1/2 of d, right? 1/2 of the absolute value of d. So this one, you can usually, if you do the graph, you can say, okay, it must be on the left side. Okay, on the left side, the whole interval on the left side, that means all the members in this interval are negative numbers, right? Okay. Now let's look at the next theorem. Next theorem is very straightforward. We're using the lemma, this lemma. Okay. We say, okay, we let a sequence Cn is in the interval AB if the limit n approaches infinity of Cn is equal to C, then C must be in the interval AB. So this is a closed set. If you have a closed interval, not closed interval. If you take the limit, if you have a convergent sequence, then this limit must be inside this closed interval. Okay, it will not be outside. Okay, it will not be outside if this is the closed interval. All right, you have a Cn. Cn is inside this closed interval. It will approach some numbers. This number will not be outside. If outside, it would be outside this interval, right? The Cn will be outside the interval. Okay, so we use the lemma we have already had. So since Cn is inside this interval, so that means since, sorry, I use proof. Since Cn is in this interval, so it's greater than or equal to A, right? In other words, Cn minus A is greater than or equal to 0. Then by the lemma we just proved, right? Something is greater than or equal to 0, then the limit n approaches infinity of Cn minus A, which is equal to C minus A is greater than or equal to 0. Right, the limit is greater than or equal to 0. This is just the exact, this lemma. If you have a sequence convergent D, and this sequence is greater than or equal to 0, then the limit is greater than or equal to 0. So now our sequence here is Cn minus A. Cn minus A greater than or equal to 0. So take the limit. The limit is C minus A also is equal greater than or equal to 0, right? The similar reason, similarly. The limit n approaches infinity of B minus Cn equals B minus C. This one is greater than or equal to 0. Right? Because B minus Cn is greater than or equal to 0. B is greater than or equal to Cn. So the limit would be greater than or equal to 0. So both greater than or equal to 0. So we want to show C is greater than or equal to 0. No problem. So that means C is greater than or equal to, from this first inequality, C should be greater than or equal to A, right? From the second inequality, C should be less than or equal to B. So we are done. Okay, so now let's look at the definition for the closed set. What's the meaning for the closed set? Definition. We say a set S in R is closed. That means if for any sequence in S that converges to A, if for any convergent sequence in S, the limit is A, then this A also belongs to S. Then we say the set is closed. So we say, okay, the set is closed. That means, okay, remark. We say a set, a closed set, okay, a closed set means for every convergent sequence, the limit is still in S. So this definition tells you, okay, if you have a set, this set is closed. What does this mean? Any convergent sequence in this S, the limit must be inside. The limit cannot be outside, okay? Must be inside. Then we say the set is closed. So here is one thing, one example. This set, rational numbers. The set is closed or not closed? Is closed? It's not closed. Closed means you must have the limit must be inside, okay? We know this Q is dense, right? It's dense in R. For any number, you must have a convergent sequence in Q, right? For example, for any number, we take, for example, okay. So yeah, in your, okay, so here's one thing I should say. In your homework, some problems are true or false, right? You don't need to give me the reason for the true problem. You just give me counter example for the false problem. Okay, always give me the counter example. So why this is it's not closed. The reason is if we pick square root 2, square root 2 is a real number, right? So since Q is dense in R, so we must have some sequence in Q which converge to the square root 2. But this limit, square root 2, is not a rational number, right? So square root 2 is a rational number. So square root 2 is not in Q. So you find some sequence which is converge to square root 2, but the square root 2 is not in S, not in Q. So this Q is not closed, right? Make sense? Any number, right? Remember, we have the theorem says, okay, which is called sequential dense of rationals, okay, of rational numbers, which says, okay, for any number in R, we must have a sequence of rational numbers which will converge to that number. So now we'll pick that number to be our square root 2. So you have still have a sequence of rational numbers which converge to square root 2, but square root 2 is not in Q. Okay? Because square root 2 is the limit of a sequence in Q, but square root 2 is not a rational number. Last example. If this one is closed, it's not closed. Why? Can you give me an example? Can you give me an example? Which is in the set, a sequence of in the set, but the limit is outside the set. Can you think about the one example? Then you can say, okay, it's not closed. Can you make a sequence in the set such that you take the limit This limit would be outside the set. A very simple sequence. What about this sequence? What's the limit? This one is inside, right? N is equal to 1, 2, 3, 4, 5. Right? 1 over 1 equals 1, which is inside. 1 over 2 inside. 1 over 3 inside. 1 over 4 inside, right? What's the limit for this one? No, 1 over n. What's the limit? When n is large enough, it will close to which number? Yeah, will be 0, right? But 0 is not in the set. All right? This is 0, 1. The first member is 1 here, right? Then 1/2, 1/3, 1/4, 1/5, 1/6, and so on. It will be very close to 0, but this 0, this boundary is not inside this interval. So this is not a closed set. Okay, this is not a closed set. Okay, in some sense, for the interval language, closed interval means both are bracket, right? So this is called closed. But we need to generalize our interval to be a set, okay? Like this kind of things, this is a set, not an interval, right? But we can still say the closeness, right? This is called closed. This one is not closed, okay? Of course, we have other examples which is closed, okay? For example, the national numbers, which is closed. It's discrete point. Discrete point, but it must be closed, right? For example, you pick up arbitrary point 1. Okay. If you pick a sequence of 1, 1, 1, 1, 1, 1, 1, this is in the rational number, right? So this limit is 1. The 1 is inside, right? 1 is a national number. Okay. Okay, so the first thing you need to pick a sequence which is in this set. Then you can see a limit, right? Okay. You cannot just pick up 4, 3, 1, 4, 3, 2, 1, this kind of sequence. This kind of sequence is inside, but you cannot say, okay, the limit is 1 because you can continue, right? Okay. So we stop here. So I have uploaded the homework. Okay, you can see.